So we've spent some time writing chemical equations. We've done some qualitative work. Now let's switch back to quantitative work. This section is on reaction stoichiometry, which is a really important topic to master. If you didn't get it feeling good in your gut in high school, don't worry, we're going to take it from scratch now, and it will feel so good when we're done. Because we're not going to memorize, we're going to make things make sense. So what stoichiometry means is that we're going to relate the amounts of reactants and products using the balanced equation. If I were going to look at reaction equations in terms of individual molecules, I would say that I could relate the molecules of starting material to the molecules of products. Now, sometimes people think that's exotic because molecules are things they can't really see. I like to talk about it in terms of things you can see. I think a chemical equation is like a recipe for something. So I'm showing you a very simple recipe for a very boring ham sandwich. 2 slices of bread plus 1 slice of ham makes 1 ham sandwich. If I asked you, how many sandwiches could I make if I used 20 slices of bread and more than enough ham, you would tell me that 20 slices of bread will make 10 sandwiches. Easy, huh? That's all there is to it. Now, I could relate them in terms of individual particles. I could relate molecules using the mole ratio from the balanced equation, just like I can relate individual slices of bread and individual sandwiches using my balanced recipe. But maybe I want to scale up. Maybe I want to talk in terms of moles of reactants and products, and that's usually what we'll do. We'll talk about amounts in terms of moles, big groups of things, because individual molecules are too small to measure in the lab. My analogy with the ham sandwich then would be relating, say, maybe dozens of slices of ham, dozens of sandwiches. So again, from this simple recipe here for a ham sandwich, if I asked you how many dozens of sandwiches you could make from 3 dozen slices of ham, you would say that you could make 3 dozen sandwiches from 3 dozen slices of ham because there's 1 sandwich for 1 slice of ham. That's all there is to this. Whenever you get confused in stoichiometry problems, just think in terms of ham sandwiches. But let me just repeat one more time as we go on. In stoichiometry, we relate the moles of different substances using mole ratios from the balanced equation. So I thought I'd illustrate our study of this with some problems. You're going to learn to solve these word problems. I'm going to try to throw in some strategies while I'm at it. So here's our first one. White phosphorus, P4, burns in oxygen to form tetraphosphorus decaoxide. How many grams of tetraphosphorus decaoxide will be formed by complete combustion of 4 grams of P4? All right, now we have strategies for solving problems. So even if I have a new kind of problem, I can apply my old strategy. If you want to get ahead of me, if you want to pause the video at any point and get ahead of me, that would be fantastic. I'm going to solve this in agonizing detail with all my usual strategies. So first I'm going to say, what's the question part of the question? I want to know how many grams, where's my pen here, there it is, how many grams of tetraphosphorus decaoxide can I make? That's the question part of the question. Now, I gave you that name in words. I expect you can write the formula. When we covered a skill together, I think it's fair game to expect that you're doing that. Now, before, what we would do is say, okay, if I know how many grams, what do I need to know that? But you won't be always able to solve a problem in a linear step-by-step fashion. I'll take clues in whatever order I can get them. What I see as the central part of this problem is that I'm trying to relate the amount of one substance, tetraphosphorus decaoxide, to a different substance, P4. And anytime I want to relate the amount of 2 different substances, that's a stoichiometry problem. I relate the moles of substances using the mole ratio from the balanced equation. So the central part of that problem is that I'm going to relate the moles of P4 to the moles of tetraphosphorus decaoxide. And if I had flashing lights, I would put that as flashing lights around that. That is the central part in any problem where we're relating the amounts of different substances. Now, some people try to get through life by memorizing routines. There's going to be too much. You can't do that. What I love is that if I trust the problem and I trust myself, it will tell me what I need next. The central part of the problem is to relate the number of moles. And what do we need to do that? We need the mole ratio from the balanced equation. So the question is telling me I need to write a balanced equation. I didn't have to anticipate that. I didn't have to memorize that. The question is cueing me to write the balanced equation. So here we go. P4. Now, I didn't know that you would know white phosphorus was P4, so I had to tell you. Don't worry. I'm not going to set you up for failure. If I think you can't know, I'll tell you. I do think you know the formula for oxygen, though. You know that oxygen is a diatomic. And I know that you know how to write formulae from their names. Tetraphosphorus decaoxide. First, we get the right substances, and then we have to balance the equation. I won't get the right mole ratio if I don't balance it. Okay, so I think just a 5 there will do it. So my conversion factor there will be that for every 1 mole of P4, I will get 1 mole of tetraphosphorus decaoxide, because that's the mole-to-mole ratio from the balanced equation. All right, now we've got bits and pieces of our map, but let's see if we can hook them together. If I could connect the two boxes from moles of P4O10 to grams of P4O10, I could finish that arrow. Do you know that conversion factor? Moles and grams, grams per mole. Oh, molar mass. Yes, I know that conversion factor, so I can connect that arrow. And now we're rolling. I could know grams of P4O10 if I knew moles of P4O10. I could know moles of P4O10 if I knew moles of phosphorus. Do I know moles of phosphorus? Well, let's go back to the question and check. What the question gives me is not moles of P4, but 4 grams of P4. Now, if I knew how to go from grams of P4 to moles of P4, and I hope you know how, then I'm all set. That is what I think the important part of solving the problem is. I don't want you memorizing my routine. I want you able to think things through. That's the skill we're trying to develop. So now that I've got the plan there, now it becomes a mathematical problem. My map says start with grams of P4 and convert to moles of P4. So the question says I've got 4.0 grams of P4. And you'll notice I'm not just putting the units grams, I'm putting the substance as well. We're going to be dealing with more than one substance, so it's really important for me to keep myself clear by writing nice clear labels. Now, I need a conversion factor that's going to help me get to moles of P4. Units are your friends. Let's see. I've got to cancel grams of P4 and get moles of P4. Units comes first because they tell you what numbers to put in there. Moles and grams, grams per mole, molar mass, the mass of a mole. And I calculated that already. That's not the fun part. Using my periodic table, I got 123.9 grams of P4. Work your units like you're not the one that proposed them. Grams of P4 cancels grams of P4, and I'm left with moles of P4. Woohoo! So I'm going to report my answer to 3 significant figures. Whoops, that's a 23. But I'm going to store that full number in memory 1 in my calculator so I don't get round off error when I go to the next step. Now I've got moles of P4. Am I lost? No, I can't get lost, because on the previous slide, I've got a map. Now I'm here at moles of P4. Now it's telling me to use the 1-to-1 mole ratio to find moles of P4O10. So here we go. The results from the previous step give me moles of P4. And my map says get rid of moles of P4 and get moles of P4O10. Units first, they tell you what numbers to go get. Now, what numbers? I see a mole-to-mole ratio. Mole-to-mole ratios come from the balanced equation, where we saw that we get 1 mole of P4 for 1 mole of P4O10 for 1 mole of P4. Don't need a calculator for that. There we go. So now what? Oops, that's an O10. My map says, once we've got moles of P4O10, one more step, we want to get grams of P4O10. So, we know how many moles of P4O10. We need to get rid of moles of P4O10 and get grams of P4O10. Units first, they tell you what number to go get. I think I need the molar mass, the mass of 1 mole. And I added that up already based on the values in the periodic table. That was 283.9 grams per mole. And I'm left with grams of P4O10. Woohoo! Now I've got the unrounded number of moles in my calculator. Just multiply that by 283.9. And to the 3 significant figures I'm allowed, 9.17 grams of P4O10. Ta-da! Now, that's cool, but with fluency, you could probably solve that more quickly. You're going to love making the map because you can see that you can string it out all at once. My map said to start with grams of P4 and get moles of P4. We use the molar mass. But I don't have to stop there. Now that I have moles of P4, my next step in the map says get rid of moles of P4 and get moles of P4O10. 1-to-1 mole ratio, that cancels out, and now I've got moles of P4O10. Map says get rid of moles of P4O10 and get grams of P4O10. So if you're comfortable, you can just go ahead and do it all in one line. It becomes so routine after a while, the biggest risk is that it becomes a mindless routine. Keep your brain on while you're doing it. Which way are you going to do it? One or the other. And you're going to do the one that makes perfect sense in your head. Don't take a shortcut before you're ready. A shortcut is a long cut if you don't get where you want to be. All right, now let's go back and check that we've answered the whole question. How many grams of tetraphosphorus decaoxide will be formed by complete combustion of 4 grams of P4? Okay, we've done that. But the last part, how many grams of oxygen will this consume? I want you to think about this problem, and based on what we've just done together, I want you to solve the problem before I get there. Pause the video. All right, I see 2 ways that I can do that. Here's a new map. For method number 1, I want to get grams of oxygen. And I want to relate grams of oxygen to grams of a different substance, P4. Anytime I relate the amount of one substance to another substance, the central idea is to use the mole ratio we'll relate moles of P4 to moles of O2 using the mole ratio from the balanced equation. There's the flashing lights part of the problem. Right on. Now, I didn't do that in order. That's okay. I can start writing pieces however I want, as long as I'm done connecting the boxes when I'm done. I can find grams of O2 if I know how to convert moles to grams. And I do. I could know grams of O2 if I knew moles of O2. I could know moles of O2 if I knew moles of P4. Do I know moles of P4? Well, actually, I do. I've already calculated that. On this slide, we already had that number. So that's what I'm going to use. If I didn't already have that, I know how to go back and get it from the number of grams as we did before. Okay, so in this second part of the problem, I'm going to start with moles of P4, and my map says that next I'm going to relate it to moles of O2. Get rid of moles of P4 and get moles of O2. All right, mole to mole ratio. Where do I get that? From the balanced equation. Let's go back and look at the equation. I see that there are 5 moles of O2 for every 1 mole of P4. 5 moles of O2. Whoops, for 1 mole of P4. So moles of P4 cancel moles of P4. And that gives me, let me bring up the unrounded value in my calculator, times 5. Oops, why don't I just string along the next conversion factor? My map says then to go from moles of O2 to grams of O2. Let's make this simple. 32.00 grams per mole. And I get 5.17 grams of O2. Pretty cool, huh? Now, before I started solving that second part of the problem, I said I could think of 2 ways to solve this. That was one of them, and it's reliable and foolproof, but some of you might have done it a shorter way. This particular equation is a special kind in which the reagents combine to give a single product. So what that means is that the total mass of the product has to be the same as the mass of what reacted. We already saw that we used 4.00 grams of P4, and we calculated that we made 9.17 grams of tetraphosphorus pentaoxide. So there must have been 5.17 grams of O2 reacted by the law of conservation of mass. Pretty cool, huh? I hope that what that shows is that there's often more than one way to solve a problem, and as long as your way is perfectly logical and conveyed clearly, I'll be very happy. All right, so in this case, we assumed that there was enough oxygen to completely use up the P4. But that won't always be the case. Let's go back to our ham sandwich. If I had 2 slices of bread plus 1 slice of ham, I get 1 sandwich. So let's try this question. What if you had 4 slices of bread and 1 slice of ham? How many sandwiches could you make? Pause the video. All right, what I would say is that I would make 1 sandwich. Here's how I would think that through to myself. I would say that for 4 slices of bread, how much ham would I need? For 4 slices of bread, I'd need 2 slices of ham, right? I don't have enough ham. So I can't use up all the bread. I'll use up all the ham instead, and 1 ham will make 1 sandwich. That will use up 2 slices of bread, and I'll have 2 slices of bread left over. What if I tried it this way? What if I had 4 slices of bread and 5 slices of ham? How many sandwiches could I make? Pause the video. I bet you figured out that you could make 2 sandwiches. You asked yourself, if I had 4 slices of bread, how many slices of ham would I need? I would need 2. Do I have 2 slices of ham? Yeah, I got more than enough. I'm going to have some of that ham left over. I've got excess ham. It's the bread that's going to limit how many sandwiches I make. And 4 slices of bread will make 2 sandwiches. I'll have 3 slices of ham left over. What we've just solved is a limiting reagent problem. If you could handle it with the sandwiches, you're going to be able to handle it when we relate it to chemical equations. This is all going to make sense. We're not going to stop till it does. I can define a limiting reagent for you, but you already felt out what it is before. It's the one that limits how much product you get. The one that limits how much product is the reagent that's totally consumed by the reaction. In other words, it determines the maximum yield of the product. Determines maximum possible yield of product. I'm going to come back in the next video and we'll solve a limiting reagent problem together. What I'll also put on our Moodle page is a link to a cute little game that will help you, just like this ham sandwich analogy did, to get used to the idea of limiting reagents and reagents that are in excess, what's left over. All right, we'll catch you on the next video.